Hello everyone, welcome back to NPTEL lecture series on cycloaddition reactions. So in the last lecture we talked about the use of carbonyl ylides in 1,3-dipolar cycloaddition reactions. So we will continue our discussion on 1,3-dipolar cycloaddition reactions. Today we will talk about the utility of azomethine ylides and nitrile oxides in 1,3-dipolar cycloaddition. And when you talk about azomethane ylide, and it can exist in at least 3 different conformations. So one, you can see here, this is called W. You can see it is W-shaped ylide. Okay. Then it can also exist in U-shaped ylide. You can see that it is U. It is in the form of U. Then it can also exist in S-shaped ylides. So there are basically 3 types of ylides possible based on their conformation. And depending on which shaped ylide reacts during the 1,3-dipolar cycloaddition reaction, accordingly you will get cis isomer or you will get trans isomer. From the steric point of view, if you look at the S-shaped ylide is more stable than both U and W. U also you can see there is a steric repulsion between these 2 alkyl group, and likewise you can see here in W also you have the steric repulsion. So because of which the S-shaped ylide is more preferred while forming the azomethane ylide. So how these azomethane ylides are prepared? So for example, if you have an aziridine and if you heat it, so it can open in such a way that it can form this ylide. For example, this lone pair can come and open this 3-membered ring to form this azomethane ylide. So this can be achieved by either heating or by shining light. We will come to that little later. And one can also directly prepare this azomethane ylide from an aldehyde and treat with a secondary amine. Okay, so first it will form a iminium ion, then it picking up a proton at this stage by a base that can give the azomethane ylide. The third option is you can take an imine and you can alkylate here. N alkylation followed by loss of proton will give the corresponding azomethane ylide. So these azomethane ylides, once it is formed, it can undergo intermolecular 1,3-dipolar cycloaddition with various dipolar, or it can also undergo intramolecular 1,3-dipolar cycloaddition. For example, like what we have discussed in the IMDA type 1, that is intramolecular diol reaction type 1, here the dipolar is attached to carbon number 1. So that's why this is type 1 intramolecular 1,3-dipolar cycloaddition, and it can also be type 2 where the dipolar is attached to, here the atom 2 is nitrogen. Okay. Once you know how to prepare azomethane ylide and then do 1,3-dipolar cycloaddition reaction, what will be the stereochemical outcome? Like what we have discussed earlier for 1,3-dipolar cycloaddition, it depends on the stereochemistry of your dipole as well as stereochemistry on the dipolar. See, for example, if you take this cis aziridine, okay, if you have the cis aziridine and if you heat it, it's like electrocyclic ring opening. So under heating condition, the opening is in and out, that is both con-rotatory opening. So you will get this ester and this ester trans to each other. And if you take the trans one and do the same, now you will get this is W shaped ylide. Okay. So, this is W shaped, this is S shaped ylide. And from cis, if you shine light, then you will get out and out ylide, or if you take the trans one and if you shine light, then in and out ylide. Okay. So, here S shaped, here W shaped ylide, depending on the substituent you have in aziridine, also depending on the condition which you use, either thermal or photochemical. Accordingly, the stereochemistry of the dipole you will get. So, once you have this, then you can do dipolar cycloaddition reaction. For example, if you take dimethyl acetylene dicarboxylate, you can see here this is trans, so that trans is retained in the product. Okay. In this dihydropyrrole derivative, you will see that these two new stereocenters are trans to each other. This can be easily visualized by the dipolarophile approaching the diene from the bottom face. Likewise, if you take the W-shaped ylide, and here these two esters will become cis to each other. Okay. So, first how the dipole is generated, second what type of dipolarophile you use, these two matters in the stereochemistry. Here the dipolarophile is triple bond, so you do not worry about the stereochemistry here, but if the dipolarophile is having only double bond, then the third stereocenter also will be generated. Okay. So, now look at this imine. Okay. So, one can easily generate anion here. Okay, it is next to an ester. So, if you treat this with lithium bromide and triethylamine, then this azomethane ylide is formed and the N is with lithium. Okay. So, if you take this ylide, once this is generated in situ, then you can do a 1,3 dipolar cycloaddition with dipolarophiles like methyl acrylate. So, now the methyl acrylate, if you draw the transition state, you can see here this is the transition state. Because of the presence of lithium, it will coordinate with the carbonyl group of the ester. Okay. So, that brings this OMe, methyl and this hydrogen, they are all in one side. Okay. And this ester and phenyl group, that will be in the same side. So, that is how ester and phenyl group both are cis to each other, whereas the methyl group, that is opposite to this ester. So, methyl and ester, they are trans to each other, phenyl and methyl ester are cis to each other. So, here the chelation plays a very important role in deciding the stereochemical outcome of this 1,3 dipolar cycloaddition reaction. Now, look at this example. So, this is already chiral one. So, you can see a chiral center here. Now, if you heat it, so then this aziridine ring will open in such a way that it will generate a 6-membered azomethane ylide. Okay. So, once this 6-membered azomethane ylide is formed, then one can do a 1,3 dipolar cycloaddition. See, for example, if you do a 1,3 dipolar cycloaddition with this alpha beta unsaturated system, which is attached to a chiral auxiliary. This is called Opalser's chiral auxiliary, Opalser's sultam, and this can undergo 1,3 dipolar cycloaddition to give this bicyclic compound. Here the X is the chiral auxiliary. So, now this amide can be easily hydrolyzed or reduced, and this has been successfully converted into the natural product called quinocarcine. So, in this particular total synthesis of quinocarcine, the key reaction is the 1,3 dipolar cycloaddition between this azomethane ylide and this dipolarophile. Then as I said, one can also do intramolecular 1,3-dipolar cycloaddition of azomethane ylides with dipolophiles. That means the dipolophile should be attached to the dipole, and this dipole, as you know, can be in situ generated. For example, if you have an aldehyde and treat with secondary amine, and if you reflex, so what will happen is intramolecularly it will form this azomethane ylide, and already you have the dipolophile. Here the dipolophile is the double bond, so that can undergo 1,3-dipolar cycloaddition to give this 5-membered ring, which is nothing but substituted pyrrolidine ring. So one can also make the same 5-membered ring. For example, if you take an aldehyde and then treat with an amino acid, and here the amino group is secondary. Okay. So then what will happen? It will also generate dipole and this will undergo 1,3-dipolar cycloaddition to form the pyrrolidine ring. Okay. And look at this example. You have a double bond, which is going to be the dipolophile, and you have an aldehyde. So once you have an aldehyde, then you can in situ generate the azomethane ylide. Here the azomethane ylide is generated with an amino acid ester. Okay, and then you have to heat it at very high temperature, so it forms the corresponding azomethane ylide, and that undergoes intramolecular 1,3-dipolar cycloaddition to form this tetracyclic compound, and that has been used successfully in the total synthesis of a natural product. So now if you look at this aldehyde, okay, here the double bond is in the 7-membered ring, and you have an aldehyde. So this aldehyde, upon treatment with again the amino acid ester, so in situ it can generate this dipole, and this dipole can undergo 1,3-dipolar cycloaddition with the double bond which is present in the suberant ring, so to form this very interesting tricyclic compound. Okay. So this type of 1,3-dipolar cycloaddition really is very useful, particularly when you use azomethane ylides to get highly substituted pyrrolidine rings. And if you have two double bonds in pyrrolidine, then they are called pyrroles, and these pyrroles also can be obtained by 1,3-dipolar cycloaddition. For example, so this is pyrrole, and if you cleave the pyrrole in such a way that the top portion is the dipolophile and the bottom portion is the dipole. So if you generate a dipole, or if you generate an appropriate dipole with a dipolophile which has a triple bond, then the possibility of generating pyrrole is very high. So look at this example here. When you treat this with a dipolophile, the dipolophile is dimethyl acetylene dicarboxylate. The azomethane ylide is in situ generated through this mechanism. Now the lone pair on the nitrogen pushes the oxygen to attack the silicon. So now you will get this azomethane ylide. You can see here this azomethane ylide can undergo a 1,3-dipolar cycloaddition with dimethyl acetylene dicarboxylate to give this intermediate. Now this can undergo elimination of trimethylsilanol to give highly substituted pyrrole. This is a tetra-substituted pyrrole. So this is very simple and straightforward using this 1,3-dipolar cycloaddition of azomethane ylide, which is in situ generated, and dipolar cycloaddition, it undergoes elimination to give the corresponding pyrrole derivative. So now from azomethane ylide we will move to nitrile oxides. As in the first lecture of 1,3-dipolar cycloaddition, I mentioned what is nitrile oxide. So the name itself suggests if you have a nitrile and if the nitrogen is oxidized, then this is called nitrile oxide. So how these nitrile oxides are prepared? There are two standard methods to prepare this nitrile oxide. One is from a corresponding oxime. Say for example, you take an oxime and then treat with chlorine or NBS. So if you use chlorine, you will get the corresponding alpha chlorohydroxylamine. On treatment with triethylamine, it will undergo elimination of HCl to form this nitrile oxide in situ. So basically you can prepare this nitrile oxide in situ by adding chlorine to oxime and followed by treatment with triethylamine. So once you generate this, then you can carry out 1,3-dipolar cycloaddition with various dipolar. Likewise, the second method is a very simple method. If you have a nitroalkanes, okay, what you need is a CH2 attached to the nitro. And if you have this nitro compound and then treat with dehydrating agents like either isocyanate or POCl3 with base, it can give corresponding nitrile oxide. How does it happen? So when you take this nitro compound and the oxygen of nitro attacks the isocyanate to form this intermediate. Okay. So once you have this intermediate, then through a 6-member transition state, this hydrogen is picked up to give this intermediate. Here you can see you have the amidate. Now again this will pick up this hydrogen using the 6-member transition state to give the nitrile oxide plus amine plus carbon dioxide. The formation of nitrile oxide from this nitroalkane is because of the formation of two stable groups. One is amino group, other one is carbon dioxide. So these are the two methods which are generally followed while preparing the nitrile oxide in large quantities. Okay. So once you have nitrile oxide, how does it react and what will be the stereochemical outcome if you treat with cis alkene and trans alkene, and the resultant product, will it be useful? Can it be converted into some useful products? So if you have nitrile oxide and then treat with, for example, cis alkene, and the product, if you treat subsequently with LAH, you will get this amino alcohol. Now if you look at this product closely, at the end of these two reactions, basically you have generated 3 new chiral centers. Simple dipolar cycloaddition followed by LAH reduction. How does it happen? So as you know, now the 2 methyl groups are cis. Then when you do the 1,3-dipolar cycloaddition, obviously these 2 new stereocenters form, the 2 methyl groups will be cis to each other. Then when you do the LAH reduction, and the hydride will come opposite to this methyl group. Okay, first. Then the NO bond will be cleaved and you get the corresponding amino alcohol, 1,3 amino alcohols. One can also simply reduce this. When you take this compound and then reduce with Raney nickel, the Raney nickel is known to cleave the NO bond. So that means it will form the corresponding imine, and then imine will get hydrolyzed, and once you get hydrolyzed, you get an aldol product. Okay, this is an aldol. So from nitrile oxide, in 2 steps one can get aldol product. Okay, you don't have to do an aldol reaction. Instead of doing aldol, you can do a 1,3-dipolar cycloaddition followed by NO bond cleavage and hydrolysis, you can get aldol. And again you see 2 new stereocenters are formed in this reaction. And if you use trans alkene, the same way you take nitrile oxide, any trans alkene, and then do the 1,3-dipolar cycloaddition, and you can see the 2 new stereocenters where the 2 alkyl groups are there, they are trans to each other, and now if you cleave the NO bond followed by hydrolysis, you will get an aldol, which is anti-aldol. This is but if you reduce with LAH, and then you will get corresponding 1,3-amino alcohol, and here you will see this, these two are trans to each other and these two are trans to each other. Okay. By choosing cis and trans alkene, you will get two different products. So from isoxazoline, you can also go to get isoxazole and isoxazolidine using the same 1,3-dipolar cycloaddition. So for example, if you want isoxazolidine, and then if you do a small retrosynthesis, so this portion will be the dipolarophile and this portion will be the dipole. So now when you do the 1,3-dipolar cycloaddition, and what will be the regiochemical outcome? The regiochemical outcome is based on this HOMO-LUMO interaction, and that will lead to the 1,3-disubstituted isoxazoline. Okay. Let us see some examples. For example, if you want to make this compound, if you cleave these two bonds, okay, the left hand side portion is the nitrile oxide and the right hand side portion is your dipolarophile. So how this dipolarophile is generated? Okay, one way is corresponding ketone and then treat with LDA and quench with TMS chloride. For example, if you have this compound, then LDA and quenching with TMS chloride, you can get this one, or one can also get it from this stable compound. How? If you take this compound and then treat with LDA, it can pick up this proton, that's an acidic proton, and that can undergo elimination or opening of this 5-membered ring to give this the same intermediate. Okay, so either you can start from here or you can start from this cyano compound. So now if you treat this with nitrile oxide, it can undergo intermolecular 1,3-dipolar cycloaddition to give this intermediate, and this upon elimination of trimethyl will give the corresponding 5-membered ring. Okay. It's called isoxazole. With methyl acrylate, it will give a mixture of these two regioisomers, and this is the major isomer. And if you have methyl propylate instead of methyl acrylate, you have a triple bond, then again you will see this is the major product. 1,3 isomer is the major product. Here is an interesting example. You can see you have a pyrrolidine. So this is nothing but an enamine. So if you have ethyl acetoacetate and then treat with proline, it can form the corresponding enamine. Okay. So this enamine, if you treat with nitropropane in the presence of POCl3 and triethylamine. So the nitropropane, the presence of POCl3 and triethylamine will generate a nitrile oxide. So this is the nitrile oxide it will generate, and that will undergo 1,3-dipolar cycloaddition followed by elimination of pyrrolidine. So what you will get is initially then elimination of pyrrolidine will give your isoxazole. Okay. Then there are many intramolecular 1,3-dipolar cycloaddition known with nitrile oxide. First let us see intermolecular 1,3-dipolar cycloaddition of a chiral compound. Then we will go to the intramolecular 1,3-dipolar cycloadditions. For example, this is a chiral nitrile oxide, and then if you treat with a terminal alkyne, and this terminal alkyne can undergo 1,3-dipolar cycloaddition to form this isooctazole. Okay. The same thing, now it is intramolecular version. You have a dipolarophile and an oxime in the same substrate. Now if you treat with sodium hypochlorite, this will in situ generate the nitrile oxide, and the nitrile oxide can undergo 1,3-dipolar cycloaddition with a double bond which is present in the 5-membered ring to form a tetracyclic compound. Okay, now later, as you know, you can cleave the NO bond, you can reduce the C double bond N to introduce more chiral centers. Okay, so this is a classical 1,3-dipolar cycloaddition reaction where it is an intramolecular dipolar cycloaddition. So this is another example where you have a stereocenter, and now if you take this oxime and then treat with hyposolution, that in situ will form this nitrile oxide. Once the nitrile oxide is formed, then it can undergo an intramolecular dipolar cycloaddition with this double bond, and that can give this isooctazole. Then one can always cleave the NO bond, reduce the carbon now double bond N. If you treat this with Raney nickel and followed by hydrolysis, you will get this aldol product. And this was a key reaction in the total synthesis of wind blasting. Okay. So basically you have to start with an oxime and then treat with hypochlorite or chlorine or bromine, and followed by treatment with base. You will get the nitrile oxide, and the nitrile oxide, once it is generated, immediately it will undergo intramolecular 1,3-dipolar cycloaddition. Okay. Here is an example where it undergoes 1,4 addition. For example, the thiol, which is generated in situ. So these type of allelic thiols are known to undergo 1,4 addition to nitroalkenes. For example, this allelic thiol undergoes 1,4 addition with nitroethylene to form this intermediate. As you know, when you have a nitro group next to CH2, then this can form a nitrile oxide if you treat with isocyanate. For example, here if you treat with phenyl isocyanate, it forms a nitrile oxide, and then this nitrile oxide can undergo an intramolecular 1,3-dipolar cycloaddition to form the 5-membered ring. So basically here you see you get 3 rings, and this has been successfully used further by reduction of this isooctazole to give the corresponding amino alcohol, and later that was converted into a vitamin called biotin. Okay. So this was a key reaction in the total synthesis of biotin reported in this paper. So now let us see whether this nitrile oxide based 1,3-dipolar cycloaddition can be used to make a macrocycle. Okay. So here if you look at this molecule, there is an internal double bond and there is one terminal double bond. So both can act as dipolarophile, and you have a nitro group. That means if you treat with an isocyanate or any dehydrating agent, you should be able to make a nitrile oxide. Okay, so that's what they did. You treat with parachlorophenyl isocyanate and then base, so that will generate this nitrile oxide. So once this is generated, this immediately undergoes an intramolecular 1,3-dipolar cycloaddition, and here the stereocenter, you don't get selectivity, you get a mixture of 1:1. But no problem, because in the natural product you don't have that stereocenter. So this is later subsequently used to convert into this natural product. Basically what you do, you hydrolyze this, first you cleave the NO bond and then hydrolyze the C double bond NH to get the corresponding ketone, and then followed by elimination of the aldol to get this natural product called monosilane. So what we have discussed today is how this nitrile oxides can be successfully used in 1,3-dipolar cycloaddition, and when they are used in 1,3-dipolar cycloaddition, so they are successfully used to make pyrrolidines, pyrols, and also macrocycles. Likewise, azomethane ylides also have been successfully used to make highly substituted pyrrolidine ring. So I will stop here, and then in the next lecture we will talk more about another dipole called azides and 1,3-dipolar cycloadditions of azides with various diplorophiles, and also we will discuss in details about click chemistry. Okay, until then, thank you.